In this next section, we're going to look at another kind of related process, and that's the process of diffusion. Diffusion is related because it's to the various other processes in thermodynamics because it's related to increasing entropy. It's an irreversible process. This is where we spill dye into water. And you've heard the expression, the die is cast, meaning it's an irreversible process that cannot be undone. Your red wine spilled on your white carpet, the glass that is broken, all of these are examples of increasing entropy, and they're irreversible. And they are really a study of increasing disorder. Well, we're going to understand heat as a process of increasing disorder associated with the second law of thermodynamics, and therefore it's appropriate to discuss diffusion there also. We're just going to look at diffusion from a simple point of view. Fick's law of diffusion is given by, and of course what we have here is we have a mass that's going to be dispersing through a solvent. So we've got a substance here and we have a solvent where it's going to be dispersing. And we have the change in mass per change in time. As it's going to go along, you might want to draw this as here's something. You have a long tube, and you can watch the concentration of the substance increase as we move down the tube and as it diffuses. And it's equal to a constant of proportionality, the area, naturally, of the substance. Well, this is the diffusion constant. For the substance that I'm in, it might be water vapor in air or something like that, times the area. This would be the area of this cross-section here, times the change in concentration. That's the difference in concentration from one place to another. If we have very small changes in concentration, then I have very low rates of diffusion. So the change in concentration is very much like change in temperature in other processes. And finally, it's going to be divided by the length, because if I make the length twice as great, it'll take twice as long, or that only half the mass in a given time will diffuse that much. The diffusion constant D for water vapor in air. So this is some water vapor here. So I put water vapor here, make the tube have perfectly dry air, and I can say, how does this water vapor or steam distribute itself over time? This constant D would give that. If I put the area of the tube in, the difference in the concentration, how much concentration here, plus say no concentration here, but then the length of the tube, and this would give us our change in mass over change in time. The thing you would never guess is exactly what such a constant might be. And that, for that particular gas within another gas, this is for water vapor in air. So this is like how humidity distributes itself. It's 2.4 e to the minus 5 meters squared per second, which is the units that naturally come out of this equation. So this is Fick's law of diffusion, and I just might mention that diffusion goes back to the work of Einstein, who worked on a problem called the drunken sailor problem. The drunken sailor problem is you have a lamp post, and the sailor starts out from the lamp post, and every few seconds, every unit of time, he takes a random step in another direction, say 3 feet. And at some points he may almost come back to where he is, but on the average, if he moves randomly in all these directions, then his position will disperse. And so the probability of finding him here is incredibly high right at first, because he can only take 1 or 2 steps away. But then his probability distribution broadens and broadens and broadens and becomes much more distributed. And Einstein used that to, in his study of molecular motion and improving that matter was atomic in nature. And with that, he explained Brownian motion. And you're familiar with Brownian motion from Brown, who studied the motion of pollen when water molecules hit it unevenly on different sides, proving, therefore, that matter was atomic in nature.